Hello and welcome. Thanks for coming. I understand the time standing between you and the beer. I'll try to be a little bit entertaining as much as I can, or keep you awake so you kind of get your beer eventually. So let me start off with a question. Who here trusts their file system? Quick show of hands. If you believe in your file system, we have about 5 people, let's say. Do you know all the config options that go with it? Do you configure journaling and other means to make sure this thing is reliable and crash tolerant? So let me first scare you. Here we're going to look at the paper from 2014. All file systems are not created equal, by Pillai and the rest, who did a study of 6 common Linux file systems. So X, ext234, BetterFS, RiserFS, and don't remember what was the 6th. And they looked at the basic properties. So file systems, what do they provide, right? So it's your basic means to store something on a disk. So you have the file system abstraction. What kind of guarantees do they have? So you basically have a POSIX standard, and file systems kind of implement the APIs sort of this way. But what that really means. So what is went on to study actually the properties that the file system have, and whether those properties hold under different error conditions. So say they decided to kind of stress test those file systems, and they built an application called blocked order breaker, which they then used to inject the errors into the file systems. And what they found was this. I'm sorry, at the back you can't read that. It's just directly copied from the paper. So basically, they studied the file systems and the properties under 2 different axes. One is atomicity of certain operations, like writing a single block of data, writing multiple blocks of data, and then the atomicity of the instruction. It's like, can you do atomic rename of a file, or atomically append to the end of the file, or this stuff. And what basically they found in all the tested configurations, which they had about 16 different ones, that all of the file systems exhibit at least one error, at least on one of the axes. And some of them are really horribly fail on almost all of them, or on all of them. So that's first finding. So your file system, the common ones, even the ones that are default in operating systems like Linux, are not reliable, or at least not reliable in the configurations they used. Like if you look at the data journaling bits here, I'm not sure, this doesn't work. So the data journaling bits here just have one error until multi-block append and writes. The rest is good. So you can get some levels of guarantees and reliability of them, but prepare to be surprised. But that was just one part of the study. And that's the basic proof. OK, this is the building block. But people don't use file systems directly. You interact with applications. You build applications on top of them. So how does your application handle errors? So for that, they built another program called Alice, where they inject error into the application. And they took a couple that you might recognize from here, like Git, Mercurial, a couple of databases here, and they subjected them to faults injected at the file system level. Like what happens if certain writes are reordered or errored? So you get an error from a syscall. How does the application behave, and what is the end result? Well, the end result was quite bad, because they found across all of the applications that there are multiple errors that they're subjected to. And then final conditions were like from silently ignoring errors, or silently not giving you the data, to data corruption and data loss. And like imagine you have a Git or something, and then you lose your data. So all your commits and stuff just poof, disappeared. So, and that's a horror story number 1. If that still doesn't scare you, and you still believe that stuff is good, we can write stuff to disk reliably, well, let's look to another paper. Because 2014, it's like 6 years ago. I'm sure all the problems have been fixed. People thinking about BetterFS maturing, ZFS and whatnot. So sure, good stuff. So in this research, redundancy does not imply fault tolerance. Researchers did a different spin. So we have distributed systems, distributed data storage systems in particular, and they have cluster of nodes, right, for redundancy. So you have multiple copies of stuff, you have clusters with leaders and followers, and everything is cool. And there've been lots of research going on. There is a Jepsen.io and where people start awareing of like what happens if network partitioning goes, we have experience in network partitioning, what happens to the distributed system, and people actually addressing those problems. Well, what these guys did is like, what happened to our distributed system, which is super high available multi-node thing, if we just have one single file system error? Just one that thing. So what they did, they started I think they started actually 8 distributed systems, and they found this. Lots of text, but basically all of them fail. And some of them fail catastrophically, where a single corrupted node can infect the cluster and take down the entire system, and make it unavailable. But what's also important and interesting, by the way, those of course have versions that particularly been tested. I'm sure that most, if not all, of the problems that they found in their research have been already addressed. But what's generally more interesting, what they found is that although you have a distributed system which has redundancy at its core because you have multiple nodes running, the advantage of using this distributed system to handle things like file system error is not there. So those systems don't have protocols to say, okay, this thing is corrupted. Well, I'll just blow up. This node is going down, and if the node is leader, the whole thing is just somehow. Or I have this error, and I'm the leader, so I'm going to infect all the followers. So, and they kind of come up with this like list of 5 things that they think that systems are doing bad, and kind of direct where we should kind of direct the research for doing these things. Okay, if you have a fault-tolerant distributed system, maybe you should also include like a protocols for recovery of corrupted data, and especially if it's like metadata and some stuff that sometimes lives in one single copy, and then this thing goes back. All right, so yeah, I'm not writing distributed system. My thing is a website. I'm just a simple backend developer, whatever. It doesn't affect me. And by the way, I'm using ZFS. Well, for that, I'll leave you with this quote. I'll give you some time to read. So don't use it. Okay, so I give you the problem, right? The problem statement. So write on the disk, unreliable. If something written, you have distributed system, the whole thing might crash and burn. So basically we're talking about 2 different problems here. One problem, how do you detect such problems? So like, how do you know that something is corrupt? How do you know the data is corrupt? And the second problem, how do you recover from it? I'm going to touch on the first one, the detection bit. Corruption, you basically look into distributed systems, into a cluster of things, and build in protocols on top of a cluster to kind of, where do I get my data? Which node has a good data? How do I know that the data is good again? Thing. So how do you detect those things? It's, of course, CRC. So we are back to the basics. For those who forgot or didn't know, if you look at Wikipedia, which is a source of human knowledge, right, as everybody knows, and you can trust everything, nobody can edit the page, right? Anyways, cyclic redundancy check. So an error code technique, so you run checksum over the chunk of data, you attach this checksum together with the data, and then you send this data over, for example, then you read the data, you do the checksum again using the same algorithm. If checksum match, there was no tampering with it, data didn't broke. The same works with persistent storage. You write it to disk. At some point, you run, I don't know what, recovery, checksum, validator, whatever, or simple program that, let's say, database starts up, reads from disk. Is it still valid? Is stuff still good? Okay, so I want to do CRC. In particular, I want to, just doing CRC and kind of like describing it in terms of hand waving is a good thing, but it's not that useful. So let's say you are building a distributed system, or you are kind of building a part of it, or using like a basic building block called a log. Append-only sequence of records written, not overwritten. You always continuously write into the same thing. So you write in a log. And so when you write the log, you want to do checksumming of the log. And then let's say you replaying the log because you need to replicate this to another machine, or you want to compute something over it because it's event-driven architecture, whatever. You want to verify those CRC. I'm going to talk about a thing that I've done for Aaron. So I've been adding a CRC support to Aaron archive, where it's basically adding CRC to the log and then to the replay part when you read from it. So let's say you want to do CRC in Java. In particular, Aaron targets Java 8 as its minimum. So I guess if I ask for quick show of hands, who runs Java 8 in production? Who runs Java 8 in production? OK, 85% of people. The rest is either not Java people or run something else, maybe Java 6 or 7. I don't think anybody runs 11. Maybe there are a couple brave. So let's say I want to do CRC in Java. Obviously, you have to go to Java util zip package, right? It's obvious to everybody that that's where you find those things. I don't know how people writing core libs in Java actually come up with these things, but things end up where they are. So you're looking at this interface like, OK, well, very Java-ish, because it kind of gives away that this thing has a state. So you kind of, when you create one and you update it, then you get a value, then you have reset method, so kind of reuse it, maybe not. But what is puzzling is that it only works for arrays and a primitive int. What if, or a single byte-ish kind of, 4 bytes, whatever that int is, up for interpretation, is it really 4 bytes or just 1? It's 1, but anyways. Anybody who worked with Java NIO knows that core abstractions of Java NIO is actually byte buffers. Java 8, there is no byte buffers here. Byte buffer was added in 1.4.2. So am I missing something? OK, wait, let's dig deeper. Of course, if you go to CRC 32 and Adler 32, there are 2 implementations of this interface in the whole JDK. You find that it has method with a byte buffer. Kind of, sort of. If you kind of squint a bit and read what's in the middle, or kind of read the signature closer, unlike this guy, where you see the byte array has an offset and a length, you can actually point out to a chunk of it. And the byte buffer, you kind of start with whatever the current position is. By the end of the update call, your byte buffer moved. So it mutates your data structure. This thing is supposed to read some bytes of it. Like, why not provide an absolute length and then offset and length like you do for the byte array? And this is Java 8, right? So the method was added. Funny enough, both implementations got the same method with the same signature. This is Java 8. We have default methods. Why on earth you don't put it into the interface as default method? It's like, you're doing the same work twice, declaring the same thing. Why not just declare it once? Well, of course, I'm ranting. This is Java 8. And if you talk to Oracle people, they say, 6 months releases, right? So use Java 14. Of course, we use Java 14. This is the interface in Java 14. Hooray! We have our update byte buffer method since Java 9 there. And we have a convenience method for the byte array. So the other way around, it goes from 0 to the length. But I still have no length and offset, which means if you want to use it, you end up doing something like this. So first you need to get your CRC32 somewhere, call update, and then get value of it. And by the way, CRC32 stands at 32-bit value, so it's 4 bytes, and you have to basically downcast your value back to int, because this is what you're going to use and attach. You're not going to attach 8 bytes of stuff which only has 4 bytes of thing in it, and then you have to rewind the position. Well, a normal Java day, right? Java day in the office. This is kind of story. But what if the world would be a bit different? What if we would have something like a static method for CRC32, or even the same was with the address? What if your byte buffer is not on heap? It's off heap. It has an address, and kind of you can do this. Well, someone might object that, the algorithms, like different checksum algorithms, they're very sensitive to the initial value. So CRC32, for example, starts with 0. CRC32C starts with special constant, which is basically -1, all bits set to 1. Yeah, I get it. You can document it. It's not ideal consumable thing, but as a building block, this is amazing. But maybe I'm imagining stuff, right? So I'm living in La La Land, and if you look inside, like CRC32. Well, this is exactly what you see. That's exactly the API that is there, but it's not available to you because you're not supposed to do it. It's just for JDK guys. I don't know, for whatever. It's the implementation detail is private even, but it's also native because it's going to be intrinsified. What I find is fascinating, if you look at the update byte buffer signature, you will see that it has the first argument is not called CRC. It's called Adler because it's copy-paste from another class, which has exactly the same method. And it gets even better because in JDK 9, they fixed it. This is now renamed to Alder. So D and L is swapped. So probably to obfuscate the reason that it was copied. Well, this is CRC32. Nice thing, in JDK 9, they added another algorithm called CRC32C, which is, by the way, way better checksum algorithm. It doesn't have the failing conditions as CRC32 does, so it detects more problems, so it's a better thing to use. And if you look inside there, you see the same picture. The version with single byte disappears because it's handled on the Java side, but we have two hotspot intrinsic candidates. So we have two methods that are intrinsified. And by intrinsified, by the way, for those who don't know, it means that instead of running the code as written there, if you open JDK 9 and beyond, and you open this class, you'll see like huge Java methods that basically implement slicing by 8 algorithm that Intel guys wrote a couple of years back. And this is Java implementation. But this is not what's going to run on x86 platforms. On x86 platforms, this whole thing will be replaced with a specialized algorithm specialized code that Hotspot will spit out, which will use CRC32 instruction, which is basically first Intel came up and then AMD implemented as well. So to have this more efficient. Okay, well, we are looking at for a very long time at this thing. So this is just this part. So we have this. So this is our building blocks. As I kind of alluded you to and showing you the native thing, that's basically what you ended up doing if you don't want to allocate in your fast pass and you kind of, you go method handles and you call private API because there is no other way in Java. This is the way you do it. It's shameful to admit. On the other hand, there is no other way. Okay, so let's look at the implementing part. So we have this thing, but before we touch any system, we have to baseline it, right? I told you that I've done it on the example of Aaron, and Aaron has an archive module. So what Aaron is a messaging system, right? It's a UDP, multicast, unicast, and IPC transport. And it has an archive module, so you have a subscriber that can get the data and move it elsewhere for archiving, journaling, whatnot reasons. So what I've done, I've run the archive module before I touch the code. So this is just everything on my laptop. On real systems, this thing goes up to more than 100 millions a second. So this is a throughput test. So basically, there's two parts to it. One is writing to disk, so recording events. And events are really nasty. So write in small messages, so 32-byte messages, and which is really stress test because you have 32 byte of payload, and Aaron adds another 32 byte of header on it. So you're writing 64 bytes. So you're thinking you're writing 32, you actually double it. So that's the most nasty one. So writing megabytes to disk is very easy. Writing bytes to disk is where the real pain points are. So even that thing can write about 40 million messages a second, and I can replay off the disk about 35 million messages a second. Does anybody find this picture disturbing or something is wrong on the picture?
Actually, reading should be faster.
Exactly. So when you're replaying, you are reading off the disk. You're not writing to the disk. So why this is slower? It's an interesting point. We're going to get back to it in due time. So, but this is JDK 8, of course. Let's do another LTS release version, which is 11, and run it and see why you want to upgrade to 11. This is absolute reason why you want to upgrade. You're like, yes, you will get 1 more million out of writing to disk, but our replay just went down the drain. Like, yes, asking the question why. One part of it is, again, I mentioned we use them. Private APIs. One of the things that Aaron is using is a lot of unsafe to deal with native buffers and patching selectors and network stack and doing stuff because there is no other way. And what was done in JDK 9, the unsafe, as we know, it was split in two unsafes. So there is SunMISC unsafe and there is JDK internal unsafe. So there is now two unsafes, and the other one is getting new features, super cool. And now there's this duality. So if you profile it, let's say with async profiler, what end up doing is that on 8, there is no unsafe calls. They all disappear. They kind of become virtual. On 11, you see the SunMISC unsafe all of a sudden popping up and up to the JDK unsafe. Somehow the call stacks get deeper. Inlining is not happening. I have no idea. I didn't go really, really deep on that thing. But the fact is this, and then you kind of explain, like, why don't you upgrade? Like, why would I upgrade? Is my incentive make my application slower? Or, like, why? Anyways, that's the Java releases and stuff. So that's all nice. We take our CRC32, plug it in, and we see the following picture. So CRC32 slows things down substantially, and this is expected. This is like a premium you pay. You want to be sure that you can detect data corruptions and stuff, so you have to pay for it. Well, yeah, maybe not that much. It's like, okay, and writing to disk, we already write in bigger chunks, we have to go through the chunk, probably we cannot do much. But replay looks interesting because replay gets quite a hit. And what's going on there? But first let's look at 11, of course, because 11 is better, right? Wow, 11. I told you that 11 has really nice CRC32C. And if you look closer, you will see that, wow, this thing is actually faster than the CRC32. And who thinks CRC32 is faster or CRC32C is faster? Guesses? Answer C. Almost. Answer, it depends, right? So by just looking at that, like it felt really weird, but kind of for this use case, you're kind of, yeah, you probably want to go with CRC32C. And actually, if I would be running on JDK 9+, just for the quality of the checksum algorithm, yeah, I'm going to choose the CRC32C, even if it might not be the best in all cases. But I've done a test where I compare CRC32 with the CRC32C. And that's why I said it depends, because depending on the size of the input, it's one or the other winning. So on the smaller sizes, before at about 92 bytes, CRC32C is the winner. I think it's like some factor of 2 at the beginning. And then all of a sudden they swap to a point where another one is 3 times faster at 512 bytes. Like, wow. Quite interesting, if you start digging deeper and like looking, am I getting the right thing? And is my understanding correct with like where this is going? But as I said, there's different algorithms. You cannot just, they are not substitutable. You cannot just, let's say, have CRC32 on JDK 8, migrate to 9, and then read the same checksum using another algorithm. It's not going to work. So once you stick with one, you have to kind of live with it, or have an update process that replace all your checksums or whatnot. That's all possibilities. But I mentioned before that we have to go for the private API because of intrinsics. Like, just to show you how bad that thing is, you see this graph. This is the same graph, and on top of it, I added hand-rolled slicing by 8 implementation. So essentially what JDK has is static methods without any JDK magic, so plain Java as implemented in the paper. And if you don't realize how really bad that thing is, this is log scale. So there is an order of magnitude difference between the things. So if you look at the 2K, 2K is more than 10x, it's about 13x performance difference. So if you try to be a good citizen and not touch any private API and just go plain Java, no dependencies, no breakages between releases, no whatever, you can't. You really want to have what the platform provides you, because that's the whole idea, is you don't run on the platform. So yeah, we tried, it didn't work. So let's get back to the replay. So as a gentleman there noted, replay should be faster. Read off disk and do whatever. What on earth replay is doing that is that costly? So if you look, and it's kind of pseudo Java, it's not exactly the code, but replay was doing something along the lines, you're reading a chunk of data from a disk, about 2 megs, and then you process it in so-called frames or fragments. So in this particular case, for every message, for every 64 bytes, you will be basically have one loop iteration. And then you do occasional verification with checksum because that thing is optional. So if you're running on enterprise grade SSDs or whatnot, you didn't enable checksums, you're not going to get a hit. So that thing is optional. And then we do the publication. And the publication is done in the zero copy semantics. So try claim is an operation that basically claims a space in the publication buffer saying, okay, I'm going to need that much. Can I claim it? And this is an atomic operation. This is very important because this has memory fences. So one try claim has memory fences because it's concurrent. There can be multiple things publishing through the same publisher. And then at the end, when we copied the bytes, so we have already the chunk, so we directly copy it into the destination, we call commit. It's a second memory fence. So we have two concurrent operations going on here. And those end up costing, those prevent loop being unrolled, those prevent some nice inlining, some other optimizations. So this is where the cost is. So what you end up doing, you need to somehow amortize the cost. So if you think about it, there's a cost on the publisher, in the case replayer side, which prepares this publication, and there is a publisher side, the other side of it, which reads out of this shared buffer and can progress. And because we are doing one frame at a time, the other guy is spinning there, waiting for that one frame, and then another frame. So basically, they also end up contending on the cache line for that thing containing 64 bytes, and which we learned in the previous talk. It's exactly 64 bytes. So we're kind of contending for that cache line, so that's really bad. So the first idea to fix that was, let's do the batching, right? Because batching is good. So can we do it a bit different? Can we publish a bunch of bytes into the publication? First, without, so using the existing API. So the idea was, instead of publishing one frame at a time, you say, okay, I'm going to grab the first frame, not shown here, it's called handle on start, and not commit it. So you kind of reserve the space, but not commit it. So committing means writing a special field there, allowing publisher to proceed. So in the first field, the publisher keeps spinning. Then we write as many fields as the MTU size, which in this case was something like, we went for 4K or something like that. So until we reach the 4K, we commit every other frame, but nobody is spinning on that. So kind of for the replayer thread, it's exactly the same number of instructions, exactly the same number of memory fences and concurrent operations, but we do better on the publisher side. So did it really make any difference? I'm going to show you just the JDK 11 results, because on 8 it was the same. But on JDK 11, it made a difference. So it unlocked some optimizations. The code was different shapes, so JIT managed to do it differently. And we got about 1 million more out of this thing, so which is like, 5% roughly. But that's not where we want to be, right? We're not beating the recording. So scrap this. So let's try to fix it again. And here comes the beat that I want you to take away from here. Sometimes just looking at the problem again, adding things makes you reconsider the whole design, right? It's like, okay, what are we doing here? We are reading a chunk of bytes, and then we're doing some mangling with it and using the API that we already have to kind of send this chunk of bytes. But what you want to do, you want to read this chunk and just send it over. Read the chunk, send it over. So, of course, it's not that easy, because the publisher side of things is doing something to the messages. It's preparing them to be sent over the network or IPC, or there's a lot of things going on there. It's like recording things like session IDs and stuff that Aaron needs to function. So our processing becomes a bit different. So we still have a loop to go through the whole thing, because we still need to do CRC. The whole point of this exercise was to do CRC in the first place. And then we do a step called prepare frame, where we do some of the bookkeeping that was living in the publisher. So again, this is deep down inside of Aaron. This is not like super public API thing, but kind of once you know this is your application, right, you can do tricks. Like you can do like, okay, what's the problem I'm trying to solve? Can I do it? And at the end, after the loop is done, so we basically read this chunk of memory, everything's caches, everything's nice there, we go through the hot loop, we go through the same thing without touching anything else, and then it's like, okay, here the chunk is ready, ready to send. So at the end, we have this new API called offer block, and like, off you go. And it's like, of course, there's an error handling and lots of other things involved, but basically, this is the whole idea. So instead of like going this little things and kind of, yeah, sometimes you have to kind of flip things, head, like other way around, drill holes through your system, put on stuff, put on API that is not very safe, but it's solving the problem. So you're kind of tailoring a solution for the problem at hand. Like stop, think, like what is the problem at hand? How can we solve it? Like go with it. Okay. So if you look at what happened next, of course we need to measure things. And if you look at the results, finally, replay is faster than record. And it makes sense. Reading from disk is faster than writing to disk. And of course, processing and sending it over. What is also interesting is that taking the CRC over also went quite faster. So we went from 34 million messages being replayed without CRC and 21 with CRC to 49 and 30. So the CRC beat got like 25% faster. The other one got way faster, like more than 50% faster. Well, that's JDK 8. Let's look at JDK 11. Quite impressive. So if you go back, so like, okay, we're doing the same 49 as before, but replay of CRC32C. So that's where the difference between CRC32 and CRC32C comes into play. Where I told you at the small messages it's about factor of 2, and you can see just how many more messages. So you get another 30%. If you directly would compare to 8, you can't do it. But basically, you get this picture. And if I remember correctly, results from before, we had 26 replay when we started on JDK 11, which was the hilarious nothing. JDK 11 doesn't work, don't upgrade type of thing. And we are back at the same level as JDK 9. So again, because we amortized all the costs. So now all those try, claim, and commit operations that we had, let's say I have million frames or something, I had 2 million of those operations. Now they're replaced to 1. And all the 2 million of those were going via unsafe. And this unsafe calls disappeared. So now in the hot loop and the hot pass, we don't have this unsafe loop. We have just at the end when we need to release this stuff. So let me think about it. What else? Yes. So that's what basically was the journey of trying to figure out how to do it and how to do it in a performant way. And in part in thoughts. So what I suggest you do is like always stay curious, keep on digging, trying to figure out how stuff works underneath you. Sometimes you're gonna break the rules, like look inside your platform, figure out how can you access the functionality that's not available there. Maybe there is alternatives. Maybe you can solve it the other way. Good. If not, try to write your own. If you fail, you still have the escape route of kind of digging through things. And what I wanted to show as well is that it's possible, even in a mature product, in a project of any size, basically, if you keep adding or evolving it, it doesn't have to be kind of a pile of things that just falls apart. Let's say you take one aspect or one quality aspect, the performance. It's like things get slower and slower and slower because nobody cares, and eventually the thing is decommissioned and we write a new system which repeats the pattern. If you really try to solve problem, you can actually do both. You can add your feature and basically have your cake and eat it too, and also keep or even improve the performance. It's like in this case, because replay was kind of sort of on par with recording, there was 20% difference. The priorities on the project were in different place. So nobody actually looked into why is that. I mean, once you see the numbers, you're kind of like, wow, that doesn't, so my understanding, my model of the world, my understanding of what this thing is doesn't match the empirical results. And then you kind of eventually find out. And because there was a need to change that code, that led into rewriting of the algorithm, kind of rewriting, like, and bringing back where it should be. Like, okay, we're starting with a fast pace, we have a nice new feature, and it's performant as well. So with that, I'm out of content. If you have any questions, please, it's time to ask them. Questions? No questions.
So actually, what the crucial point was that you avoid these commit actions in between.
Kind of both. Not just commit, but also claiming the so basically avoiding the expensive operations. So amortizing the costs. That's what it is. Exactly.
Not in chunks.
Yeah, and depends. That was also batching, right? And it's like, at the end, what mattered was amortizing, removing those concurrent calls, right? Removing the volatile writes or whatever the thing is underneath. But that's where I think. But if you think about it, the process in the first approach was also doing batching because it was releasing the whole batch to the publisher. So the publisher saw all bytes in one chunk. At the end, publisher saw all bytes in one chunk. So at the beginning, when we start, neither of these things had a batch effect. So first solution got a batching for the sender. Sender could just swipe through all the bytes directly. And the second solution actually brought the batching to both and actually the amortizing. So you need to know where the costs are to figure this stuff out. Funny enough, in this particular case, if you run a profiler, your profiler will be all over the place. You would not find the bottleneck. It's just because Martin knows the system that well, and chatting to him can help figure out, okay, what are the leverage points and where are the problems. It's funny enough, it doesn't show up and like it is. It's not a hotspot because the thing kind of, spread around. It's multiple calls. They are done in the loop. You see, like, okay, it's probably this loop, but what's costly in this loop? What's the problem there? All right. Thank you so much. With that, you're free to go to get beer.